Hi, in this video we'll be talking about techniques to find primes in the range 1 to 10 to the power 7. So one obvious method that can come up to the mind is, let's say we would loop from 1 to 10 to the power 7, okay, one number each at a time, and for each of the number we can call the order root and prime checking method that we talked about, that we loop from 2 to root n for any n, and if any of the numbers till then divide the number, then it's not a prime, or else it's a prime, right? So with that checking for each of the numbers, the complexity that we would get is something of the sort, let's say this max number, like the max up to which you have to calculate is, let's say, capital N. So the complexity would be order of capital N root of n, right? Because towards the end each of them will have around root n type of uh, complexity to find the check. So this would be the complexity. Okay, now this is pretty large for n to be equal to 10 to the power 7, because that won't pass the time limit. This is more than 10 to the power 9. So we would need to find out some efficient method to calculate all the primes in a particular range from 10 to the power from 1 to 10 to the power 7, right? So fortunately enough, a technique that finds out all primes in a range exists, and that particular idea is called Sieve of Eratosthenes. So let's quickly have a look at what the idea is. Okay, so let's say initially we keep an array which says that is the number 2 prime, is the number 3 prime, is the number 4 prime, and so on. Like, this is a boolean array that we keep, and let's initially fill up them with all ones. Let's first assume that, okay, all of them are prime. Makes sense? So we are just assuming that all of them are prime. Now what we do is we loop from the front. We see, okay, 2 is a prime, so we mark off all the multiples of 2 to be not prime, because we know, right, that if 2 is prime and 2 is dividing some other number, then that number cannot be a prime. So we just strike them off from the numbers and we move to the next number. So we see 3, so now we strike off the multiples of 3. So we see that, okay, 6 is already striked off, so it's okay, like we just keep it like striked off. 9 gets striked off, and so on. Next we move to 5, that's not striked off, so we loop on its multiple, which C7. Okay, we don't loop on multiples of 4, because any multiple of 4, if 4 has been striked off, any multiple of 4 has also been striked off. Now why? Because any prime p that striked off 4 would have also striked off all of its multiples as well. So we don't need to loop over the numbers which are already striked off, right? So we are only looping over the numbers which are not striked off. Okay, so, and we are claiming that any number that is not striked off is a prime, because no smaller number is dividing it. Okay, and any number that has striked off is composite, because some smaller prime has marked it to be not prime, right? So this is the whole idea of Sieve of Eratosthenes. Okay, now let's look into the code part of this. So what we are first of all doing is we are like initializing everything from 2 to n to 1. Let's assume that everything is 1. Okay, and then what we do is we loop from I equal to 2 to n and I plus plus. So we are moving forward in each of the numbers. All of them are initially 1. Okay, now for every number we start with its next multiple. Okay, so that's just the next multiple, and we keep on going ahead by that same particular number if that's a prime, right? So if it's a prime, if this is a prime, let's say this is 2 and this is a prime, if this is 2 and this is a prime, so we keep on looping over its multiple. So this is the first multiple, this would be the second multiple. Okay, this would be 4, this would be 6, this would be 8, right? So we'd be keeping on looping on its multiples, and we would be marking them off as not prime, right? So any number which is 1 will only for those we would be looping over its multiple, right? So this is the whole code that you would need for like finding out primes. So is prime, after it loops from 2 to n, all the numbers that still have 1 in it is prime. Okay, and those who got to 0 are composite numbers. Makes sense? So we can optimize the code a bit by just starting, instead of starting from 2 into I, we can start from I into I. Now why is that? So let's suppose there is some number I. Okay, now there is this number I into I. Now any number which has I as its factor, okay, one of its factor, and it is less than I into I, okay. So there is some part, okay, multiplied by I, okay, and this number is less than I into I. It's strictly less than I into I, right? So this rest of the part would be less than I. Now this has to be either prime, or this will be some portion of this would be prime, right? So any number which striked off this particular p, or this particular number itself, if it's a prime, must have striked off that number from this I plus 1 to I into I minus 1, right? So that's why we can quickly optimize it on this part, that we can write it as 1 LL into I into I. Now why am I using 1 LL? Because even if I is integer, this might get into long, so we just need j to be long. Okay. Now this optimization is a constant time optimization. However, this, like in practical work, makes the code a bit more faster, because we are pruning off a lot of numbers here, right? Now let's quickly do a time complexity analysis. So this is fairly straightforward, that this particular part of the code takes order n, because we are just looping over from 1 to n, from 2 to n. Now this particular part is a bit complex. Let's understand what we are doing over here. So for each of the number I, if it's a prime, then we are looping on its multiples, okay. So even though, like, this is a constant optimization, right, this is not going to change. So we are doing almost same computation as if we are like looping on its all of its multiples. Why? Because we discussed that, okay, the number of multiples in 1 to root n is far more less than number of numbers in the part root n plus 1, because this is a bigger range. If you talk about this is a very bigger range. So that's why this particular range, even from I square to n, is still a big range, right? So this is still an like constant time optimization. So we can think about it as like looping on its multiples of I in the range n from 2 to n, which, so we are just leaving out the I1, and the rest of the thing we are just marking as not prime, okay. So if we think in that terms, this particular, for every prime p, we are looping on its multiples, right? We are striking off 2p, 3p, and so on, right? So the optimization will just make it this p square plus p, and so on. That's the only change that we are happening, right? So from there are only order p number of optimization going on over here, order p removals of terms. Still there are a lot of terms after this. So this is a constant time optimization. So if we talk about for every prime p, we are like removing all of its multiples, right? So this loop is visiting all of the multiples for all the primes. So for any prime p, the number of multiples less than equal to n is equal to n by p, right? So if we talk about the expression, the summation would be something like n by 2 because 2 is a prime, plus n by 3 because 3 is a prime, n by 5, n by 7, n by 11, so on, up to n by whatever the largest prime that is less than equal to n, right? So this is going to be the summation, and note that this particular summation turns out to be order n, capital N, log of n, okay, right? Now there is another summation that you should know about, that is n by 1 plus n by 2 plus n by 3 and so on up to n by n. This particular summation turns out to be order n log n, okay. So these are two important complexities. Now in our Sieve of Eratosthenes, we have this particular complexity in our place, right? This is the complexity. So the Sieve of Eratosthenes finds out the number, all the primes in the range 1 to n, okay, in n log n. Okay, so this is the final complexity of Sieve of Eratosthenes. So that's all on Sieve of Eratosthenes. See you in the next video.